And then we have direct control that holds extraneous variables constant so their effects are not confounded with the treatment. So all calculus classes get the same textbook. All classes take the test at the same time. That's direct control. You have the power. Okay, so let's talk about, we're going to talk through, basically for the rest of the time, rest of lecture, we're going to look at 3 different experimental designs. The first one is just a completely randomized design. The units, which remember that's the smallest basic item to which you can apply a treatment. The experimental units are assigned at random to treatments, or treatments are assigned at random to trials. So we have this flow chart that helps us to see the process. You start with your experimental units. And this is what you'll end up drawing in that blank under completely randomized design. You got your units. And then you have a random assignment into each of the treatments. So it splits off into your, assuming you only have 2 treatments. We'll keep it simple. I don't think y'all want a flow chart that's like 8 treatments in width. And then for each treatment, you have to measure the response. And then you compare the treatments. So on our herbal supplement example, the experimental units were the people. One took the supplement, one took a placebo. They took measurements for each, and then they compared. So that's the process for completely randomized design. So let's look at 2 examples of a completely randomized design experiment. And I still see some writing, so I'll pause for a second until I get caught up. Anyone still trying to get it written down? Are you trying to get the chart written down? Mm-hmm. You're good? Okay. I just didn't want to switch it. Okay, let's look at a fertilizer experiment. So a farm product manufacturer wants to determine if the yield of a crop is different when the soil is treated with 3 different types of fertilizer. So they're going to have 15 similar plots of land that are going to be planted with the same exact type of seed, but are all fertilized differently. At the end of the growing season, the mean yield from the sample plots is compared. Just as a reminder of terminology, you'll hopefully know this already, but or remember, I should say, what's mean? Mean? Yes, average. So they're going to look at the average yield from the sample plots. So what are our experimental units in this case? The plots of land, that's right. That's what we're going, the plots of land are what we're going to apply the treatments to. What about our factors? Which, remember, factors are the same as treatments.
Types of fertilizer?
Types of fertilizer. Perfect. There's 3 different types of fertilizer. What about the response variable? What are we measuring? Well, we're measuring the yield. Yep. The yield of the crop. At the end of the growing season, the mean yield is compared. And last but not least, how many different treatments do we have? 3. 3 types of fertilizer, 3 different treatments. Questions on this part of this example? Okay. So we're going to continue it. Same process, or basically same thing, same experiment. We're just taking it a step further. Why do they use the same type of seed on all 15 plots of land? Yep. That's right. So what are we trying to do? Have what over the experiment? Control. It's part of the controls in the experiment. Just like that textbook in our calculus test example. Part of the controls. So what are some other possible variables that could impact our yield? Watering, sunlight. What else? The soil. Yep, that's a big one. Soil, water, sunlight. Last period said insects. You have insects in the ground. Yep, those are all types of variables that could be extraneous. Do we have a placebo? Explain. No, we don't. Do we need a placebo for this experiment? No, they're plants, that's right. Well, the placebo would be the fertilizer, but still, I mean, okay, let's go just buy some random granules and throw it out there. Spray them with water and say, oh yeah, it's fertilizer. Yes. And the placebo is not needed. Now this next example, I mean, some of y'all may have, I don't know, but y'all may have done something like this at home. If you make cakes and you want to figure out what kind of pan works best, well, a consumer group, that's exactly what they wanted. Which cake pan works best and bakes the cake the most evenly? So they test aluminum, glass, and silicone pans in both gas and electric ovens. And to do this experiment, they bought 30 boxes of cake mix to use. So what are our units? The cake mixes. Those are our units. Yes.
If there were different bakers, would those also be experiments?
Different what?
Bakers,
Bakers, we don't know that there are, so, but yes, that would, I don't know that would be the unit, because the unit itself is actually what you're applying the treatment to, where that would come in is in factors. Yes, Will?
Wait, why is the cake mixes the experimental unit?
Why are the cake mixes the experimental unit? Because they're what we're actually trying to look at the evenness of. So we're going to mix the cake, all these cakes up, and then bake them in different conditions. So if you think back to like our calculus example, we had the students as the unit because they were, I'm wrong. The sections as the unit because each class was going to test at a different temperature, right? So an experimental unit is the smallest item that you can apply a treatment to. In our case, the cake mix is the smallest item that we can apply treatments to. Does that make sense? Good question. Where am I? Now, so we said cake mixes are the units. What are our factors? Or what are our different treatments? Types of pans and types of ovens. Yes. We've got two factors, pans and ovens. I think they probably wrote this problem about my mom's kitchen when she was first baking cakes. Because she tried every kind of pan to get her cakes to rise the tallest. Like you open her cabinets by her oven, there's just tons of cake pans. It's like, Mom, you haven't baked cakes in 10 years. But I might need that pan. Seriously? You need a Thomas the Tank Engine cake pan. Well, if I have grandkids, I might need to bake a cake for them. Okay, Mom. What's the response variable? What are we measuring? Yeah, that's how much it rises, how evenly it bakes.
So the cake itself.
Yeah, the cake itself is the response variable. That's right. Is the middle still gooey and raw, but the sides are burnt to a crisp? Which, at least from my experience, that's pan, that tends to happen. Okay, name our treatments. What are all of our treatments here? Yep, that's exactly what I mean. So we have aluminum with gas, aluminum with electric, glass and gas, glass and electric, silicone and gas, and then silicone and electric. Yep. We got 6 different trouble treatments. And I'm just going to apologize for this next example. It is not a pretty one. You may want to start, if you're done writing now, you may want to start exercising your fingers, massaging your hand, getting it warmed up. And one thing, what I may do this time, last period, we just talked about it. What I may do is get y'all to actually start trying to design it ahead of time, and then we'll talk about it. So there's some that are trying to finish copying this down. Those that are done, the next example is continuing from this cake experiment. They want you to describe how to randomly assign cake mixes to the treatments so that there's an even number in each treatment. So how could you design it to where there's basically 5 boxes of cake mix in each treatment? And try to be as detailed as possible when writing your answer. If you need to, you can talk it out with your neighbor. See what they've come up with. I want y'all to figure out how to do this to where it's random, but yet we end up with 5 in each treatment. Give y'all, let's see. I'm gonna give y'all 2 minutes to try to figure out a process. Yes, you may.
Mr. Schultz,
Uh-huh.
can you explain what we're doing? I wasn't quite here for all of it. What exactly is this?
Okay, so we have a cake experiment that we're trying to figure out. We've got 30 boxes of cake mix, right? And there are 6 different combinations of either pan or oven. How can we randomly assign those 30 boxes to where each of those combinations has 5 cake mixes?
Okay.
Does that make sense?
Just kind of like describe how to do that.
Yeah, try to describe how to do it using as much detail as possible. Think of it like you're trying to tell someone next door in Mr. Anthon's class who knows nothing about what we're doing. How can they do this experiment? I'll give you another couple of minutes. Yes. Write it down. I'll give you another couple of minutes.
She did.
Yes, she's here. You can. Another 30 seconds. And then we'll talk about it.
I'm not sure what to do.
There's going to be a really detailed explanation on the screen. So, will also be posted. This whole PowerPoint's also posted in Blackboard and Google Classroom. So. Okay, so what are some of the ideas that y'all thought of? How would you describe how to do this to someone who just walked in the room? What could you do? Let's see what they say. So number the boxes 1 to 30. Write the numbers 1 to 30 on identical slips of paper and place into a hat. Notice there's that word popping up again. identical to keep it completely random. Place into a hat, mix well, then randomly select 5 numbers from the hat and assign those boxes to the treatments of aluminum pan and the electric oven. Then you randomly select 5 more. Assign those to aluminum pan and gas oven. And we continue this process randomly, assigning 5 boxes to each treatment until all the treatments have 5. Let's see, will that cover it up? That's okay. Thank you, David. I just wanted to save that link that you shared yesterday. So some last period wanted to just take a picture of it. Some said, I'll write that at home. It's on Blackboard or Google Classroom, right? So I'll give y'all a few minutes in case you want to write it down, take a picture of it. So I'm printing it off and taping it in there. I'm not writing anything. Save this link David sent. While y'all are writing, another reason that people often care about how evenly a cake bakes, especially the bakers that are baking to sell, if a cake has a huge crown on it, you gotta cut that crown off to ice it. Well, you cut the crown off and you're selling the cake, you're just throwing that crown away in most cases. So when you throw ingredients in the trash, you're essentially throwing money away. Or you're like my mom who wraps it in foil and then my dad eats it for breakfast with coffee the next day. Anyone still trying to write it down? No. Okay. We've got one more that's going to have a lot of writing, but that'll be it. This is just one of the ways that we could perform the experiment. So what about rolling a dice for each box? So if we roll a 1, we assign the box to the first treatment. We roll a 2, we assign it to the second treatment, and so on. Y'all think that would work? You could not get even numbers in each one. Yeah. And then you would also have the problem that the boxes themselves need to be random. So if you just have them lined up 1 to 30, and then 1 goes here, 2 goes there, 3 goes, then the only thing that's random is the dice you're rolling, hopefully. So you gotta also randomize the boxes. Then you could roll the dice. Because also those boxes could have been made at slightly different times, and maybe you happened to buy 30 that were one right after the other. Just again, randomize, randomize, randomize. Okay, the next type we're going to look at is a randomized block experiment. And we're going to have another chart here to draw. The units are blocked into groups, and then they're randomly assigned to treatments. So this is like where we had to block by the professor on that calculus example. And then of those classes that each professor had, they were randomly assigned the 65-degree room or the 75-degree room. So you've got your experimental units first. Basically, in that example's case, you have all 10 calculus classes. Then you split them into 2 blocks. You create your blocks. Once we go to blocks, within each block, you have random assignments to the 2 treatments. Assuming there's 2 blocks and 2 treatments. You can imagine how messy this diagram would get as you add blocks and treatments. Then, once you get your treatments figured out and you start treating them, you'll measure the responses for each. So if that's the calculus test, the way that would look is you'd split them up, they'd take their test. The measurement would be the actual grades on the test. So you could see that in this time frame, it may take a while. By the time they take their test, then you score all their tests, It may take a little bit for everything to be released. Then, within each block, you compare the treatments. So in block 1, you compare treatment A to treatment B. In block 2, compare treatment A to treatment B. And then you bring it all together. So you compare the treatments, or compare the results, I should say, from both blocks. Bless you. So notice that on the blocks, units should be blocked on the variable that affects the response. So in our, again, going back to the calculus example, we blocked on professor because different professors could affect how well the students do. Some professors could be easy, some could be hard. And as you go off to college, I highly recommend looking up the site Rate My Professor. You could create an account and rate professors as you go through college, but then also it works the flip side. When you're creating your schedule, you can look up the professor on that site and see what others have said about him. Like I can't, yes.
So you can choose professors?
Yep, in college you can choose professors for the most part. For the most part, you can choose professors. Where it gets almost to the point where you can't choose is, let's say you have to take one class this semester and there's only one professor that teaches that class. Well, then it looks like you're stuck with him. But yeah, you get to choose professor, you get to choose when you take the class, if there's multiple times. But what I usually went by, or I tried to go by, is first professor, then time. If the best professor is at 8 in the morning, it looks like I'm getting up at 8 in the morning. So yeah, you get to choose the professor and the time you take the class. And I almost signed up for a Texas government class, and then I read those reviews, and they were like, no, don't take it with him. He wrote the textbook. Like, okay, he wrote the textbook. What's the, like, he lectures way off the wall and then tests you on very small details in the textbook. And that's all your grade's based on, is the 4 tests you take in his class. So if you can't remember what you read, don't take him. I'm like, okay, drop. I'm not taking that class. I took it I ended up taking it in 2.5 weeks during a May mini-mester at Blinn. I did not want that professor. And they said he's very, hopefully I'm not like this, but they say he's very monotone and boring. If I ever get to that point, y'all just tell me. Okay, so let's take the randomized block experimental design and apply it to our fertilizer scenario, but we're changing something, or we're actually changing two things. We lost the type of fertilizer. Now we're down to 2 types of fertilizer. However, we just purchased more land. We have 20 plots of land now. 10 of them are along a river, and 10 are away from the river. And they're planted with the same type of seed, but fertilized differently. At the end of the growing season, the average yield from the sample plots are compared. So, can we directly control the type of soil in each plot of land? No.
Choose 5.
You what?
You choose 5 from the ones next to the river and 5 from the ones away from the one block.
That's right. No. You can't control the soil. You must use the plots that are available. So, if you've ever went to like close to Lake San Rayburn or close to one of the rivers, Natchez or the Angelina, and start digging deep, you'll find that when you get close to a body of water, you'll actually start hitting water, but sooner when you're close to a river. Like your hole will start filling with water sooner than if you were in the middle of the county away from all the rivers. So there's more water in the soil, and often bacteria and bugs and everything else. So what can be done to account for this? We've already mentioned. You could block by type of land. Okay, so now we've got to design the experiment again. So describe how to create the blocks of land and then randomly assign plots to the 2 types of fertilizer. So if we look back at our process that we drew out on the bottom of the previous page, what's our first step in this experiment? What did we have to do first? We got to create blocks. So create 2 blocks of land. Block 1 are the 10 plots by the river. Block 2 are the plots away from the river. Then, once we have our blocks, We number the 10 plots in block 1 from 1 to 10. Write the numbers on identical slips of paper and place them into a hat. Mix them well and randomly pull out 5 numbers. And assign those boxes. No, shouldn't be. Correct that typo last period. Assign those plots to fertilizer A. The remaining 5 are assigned to fertilizer B. So now we've got block 1 done. What would we do for block 2? Same thing. Use a similar process for block 2 as we did for assigning treatments in block 1. We've got one more type of experimental design to talk about, but you don't have to draw a chart for this one, and there's not too terribly much to write either. We're on the home stretch. While some are finishing up, I'll just kind of talk about the definition part of the next one. So for matched pairs, that's our third one. A special type of block, it's a special type of block design where the blocks consist of 2 experimental units that are similar, with each being randomly assigned to a treatment. So each block has 2 units in it, a pair, and they're randomly assigned. Or the block consists of individual units that have to do both treatments in some random order. So this is what I was just mentioning. You may want to circle on your notes handout the word "or," just to help you realize there's 2 different ways we could design matched pairs. You could have blocks that consist of 2 units and assign them randomly, or individual units, but then they each have to do both treatments. Okay, last example. We have this word processor experiment, which basically things like Microsoft Word and some other competing software. 2 new word processing programs or to be compared by measuring the speed, not the spread, the speed with which a standard task can be completed. 100 volunteers will perform the same task on each of the programs in random order, and their speeds will be measured. Why is this a matched pairs design? Why does it fit our definition?
Because the volunteers have like a sense of randomness and how evenly matched and processing, word processing stuff and testing.
Yep. So each block consists of an individual who will do both word processing treatments. What's a way we could determine which program they use first, though? What's something we could do?
Okay, which 50 does 100 volunteers, 50 does one volunteers, and 50 does 100 volunteers.
You could flip a coin. We want to be as random as possible because they're all going to do both of them.
Yeah.
So the best way would be to flip a coin. So flip a coin. If it's heads, they do A first. If it's tails, they do B first. And then you could use a random number table. Just go through and, the first person, look at the first random number. If it's odd, maybe they do A first. If it's even, they'll do B first. If it's 0, you just skip it. So there's other methods. Did everybody get the blanks for the slide? Still see one writing. 2, 3. Regardless of the type of experiment that you do, the only way that you can show cause and effect is with a well-designed, well-controlled experiment. It's going to be well-designed and well-controlled. That was the next slide. But not well designed, not well controlled, then you can't say one causes the other. So with that, the end.
Oh, would you mind?
Sure. And they lived happily ever after. Yes. Coming that way. I guess let's talk through. First, split them up by, what was it, last time? Oh, first order. So let's split them up, first order, last. Or are they really, other than that one feature, are they really grouped by anything distinguishable? No, you're gonna get all. There's not one thing that they would have in common, right? So when we look at our definition for stratified random sampling, do we want them to have something in common, or do we not really want them to have? They won't, yeah, they want to be based on some characteristics. Look at, they put them into college students, non-students who work full-time, and non-students who do not work full-time. So now look at that. They have only students. Are they leaving anyone out? Yeah, everyone who's not a student. So would that be a good one to pick? Yeah, they're leaving people out. Okay. 3. They put the residencies of South strata by randomly assigning residents to one of the 5 strata. That's right, they're not leaving them out. Let me just double check before I say, yeah, that's it. Let me double check. So what number was that? 2.30?
Yeah.
Okay. Let me get double check.